So welcome everyone to Guided Study Group Week 11. And so as Dr. Kasha said, this is the last week of the materials for Math 141, and next week is going to be the final exam review. And so let's get started. Today we're going to be working on mostly polar coordinates, and it's kind of like, again, working on, converting it from Cartesian coordinates, and just kind of like 10.4 is going to be on finding area using polar coordinates. And so first of all, 10.3. Polar coordinate system is the 2D coordinate system with each point denoted by r and theta. And it also are the two coordinates of every single point, with r be the distance from the origin and theta be the counterclockwise angle required to reach the 0-degree RA, or the x-axis. And some other thing to note is that negative r theta. So negative r theta. So say this is the theta line, and if you have this negative r, this is not it. This is that. So negative r theta. This one is equal to theta plus 2r theta plus pi, as seen on the graph. And so we also have a point can have multiple representations in polar coordinate system because the angles stay the same as you go every 2 pi's angle, and so you can have multiple representation because of the different angles that can be represented, because of the one single angle that can be represented different ways. We also have connections between polar Cartesian coordinate system. So similar to parametric curves, when we learn about polar coordinates, we'll usually try to put it into a transfer between polar coordinates and Cartesian equations. And so to do that, you're gonna substitute x equal r cosine theta, and that's very simple if you're just looking at the following graph. When you have any single point, and this is the r and this angle is theta, and this is your x and this is your y. So this one's r cosine theta and this one is going to be r sine theta. Now tangent theta, if existed, is going to be y over x, as we always have rise over run, and that is what we also call the slope of the line made by the origin and that point. And then x squared plus y squared. If you replace x and y with r cosine theta and r sine theta, the expression of sine square plus cosine square of any angle will equal 0, will give you the fact that x squared plus y squared is equal r squared. We are sometimes having polar coordinates given in the form of r as a function of theta, and so to graph those curves, we need to work on the frequency, special points. So the frequency is like how long does it take for the graph to repeat itself again, and sometimes it's 2 pi, sometimes it's pi, sometimes pi over 3, depending on is it some function of theta, or is it sine 2 theta, or is it cosine 3 theta, some things like that. We check the special points, and the one I usually use is and the one that I usually use is yes, give me a second for this. Just kind of okay. And the special points I usually use is 0, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4. Sometimes it's 5 pi over 6, and definitely you have pi and then 2 pi. Most of the time you don't even need to go that far to 2 pi, but from 0 to pi, definitely you usually gonna need it. We also have check the initial and terminal points. Sometimes it can give us a very quick hint about if we're talking about a right graph or not. Or the best way is that you have a tables of values and you're just gonna check by all of that. We also have, you can also graph them based on the symmetry of the graph. If you have, if the polar equation is unchanged when you replace theta with negative theta, it's symmetry about the polar axis, which is also the x-axis. And if r is replaced by negative r, it's symmetry about a pole, which is the origin. And if it doesn't change when you replace theta with pi minus theta, it's symmetric about theta equal pi over 2, or usually it's the y-axis. Some problems that you can be asked in these sections: convert a point from polar coordinates to Cartesian coordinates using the expression we're given. Find Cartesian for polar one. Know the shape of the common graphs. So sometimes you can be asked, and especially when this is a multiple choice exam, not only do you don't really have to graph them out by your hand every single time you ask to find the graph. Usually you're gonna be asked, like, say things like, what is the graph of this polar coordinates function for polar function? And so you must, usually the case is that you should know the common graph. Even if you're not asked to graph it, and just identify what graph is your function about. It's always save your time if you know the graph, and then just, maybe there's some adjustment, like shift it up a few units, and some things like that. And so let me So the first example is to sketch the curve r equal 3 sine 3 theta. And so the way that I usually do it is just start it with the special points, and then gonna go up from that. So we have pi over 4 first, and then 3. And then you have 2 pi over 3, 3 pi over 4, 5 pi over 6, and maybe pi. And so let's start it with r. You have 0, 3 sine of pi over 2, which is going to be 3, sine of 3 pi over 4, 3 square root of 2 over 2. This one 0, negative 3, 0 again, and you can guess it for the rest. And so if you do that, your graph is going to end up with, I'm just going to do it once because after that you're going to see the repetition. So it's starting from 0, then go to pi over 6, and this is pi over 3. So this is starting at 3 here. Then you go from pi over 2, which is pi over 4, which is like this. It's going to a smaller value. And then at pi over 3, it's going back to 0. So you go out, you go in. And then you go at pi over 2, r is equal to negative 3. So it's going this direction instead of that direction. And so you're going down. This is 3. You go back to 0 again. And as you can imagine, let's do the rest for here. Instead of trying all these values, let's just do 5 pi over 6 and then pi. So for pi over 6, you're going to have sine of 5 pi over 2, which is going to give us 3 again. And so 5 pi over 6 is this angle. And so you get 3 here, and then this one is going to be 0. You go back here, and then you have 0. And then it's just 0 to pi, and if you repeat the table from pi to 2 pi, you're going to notice the same train. And so that is the way we usually graph when you have a lot of points, but you can easily see the train if the graph is going to repeat more than once on from 0 to 2 pi. Let's redraw this one. Okay. Now, similar example, but let's sketch the curve r equal cosecant theta. Now, a lot of you might try the tables again, but I'm showing you different ways that you can graph it without, just using one technique. And this is going to be a second technique. You have no idea how the graph of cosecant look like. And that's usually the case because cosecant is 1 over sine. And basically to do that, you have to kind of like flip with every single point in 1 over sine, and sometimes there's the there is the undefined point. But this is a second way where you, instead of graphing it in polar coordinates, sometimes you can do it with r sine. You can, so what I just did is that I multiply sine theta for both sides, and I end up having y equal to 1. And so that is the technique here, is to try to put it into a Cartesian equation, and just it takes you like 1 second to graph it. And so that is the second technique, and this is also the graph of your functions. This one, in this case, we always assume that let me do this. There's a problem with this machine right now, and I really have no idea how to resolve this part. And so in this case, our assumption is that sine theta is different from 0 and it is defined without fraction. Now, finally, let's go to this example. Again, I have no idea how cotangent and multiply cosecant look like. And what I will do is that I'm going to try to put it in the form of the Cartesian equation again. In this case, to know what exactly I need to multiply, I'm going to expand what is cotangent and cosecant. Cotangent is cosine theta over sine theta. So it's going to be cosine theta divided by sine square. Now, I will have r sine square theta equal to cosine theta. If you remember, r sine theta is y, and I still have theta left on each side. So what I do is that I'm going to multiply r again on each side. You can do it this step, or you can do it even before that at this step here, step 1. But after that, what you end up having is that you're going to have y multiply x is equal to y squared is equal to x. That is the graph, and to do that, we're going to have x equal y squared, so it's going to look something like this. So that is your curve, and by putting it in coordinates, Cartesian coordinates, it makes life easier to resolve it. But sometimes note that you don't just, multiply the denominator over and you resolve it. Sometimes you have to multiply some extra thing to make sure that all of the theta disappear, and all you end up having is just in x and y. Now that's everything about 10.3 mostly. Now we're going to work on 10.4. So 10.4 is kind of like the application of polar coordinates. Why do we need to use it? And so I will give us a hint here. In what 230 and 231, when you learn about things in 3D, you're going to learn like kind of like an advanced system of this kind of thing. When you learn about cylindrical coordinates, you're going to have another dimensions to it. And so at that time, you're going to be able to use it for more purposes and maybe try to find the volume of a 4D solid. But in this case, first you're going to start up with area in polar coordinates. I think in the first few sections of 230 and 231 is where we're going to work on finding the area of, finding the volume of the solid using polar coordinates. And so to do that, first of all, let's starting with the area of a sector of a circle. And so we all know that this area of a circle is pi r squared, which is going to be half of 2 pi when you have a circle span the 2 pi angle. Therefore, when you have a sector of a circle that is bounded by the angle theta, your area is going to be half r squared theta. Now, if you have S be the region bounded by two curve, and like it's this angle, and your graph doesn't have to look at a straight line, it can be like a curve as we just have in free sine free theta, excuse me. And so your area is going to be half the integral from a to alpha to beta of f theta squared minus g theta squared. And so in this case, f theta is going to be the outer radius, and g theta is going to be the inner radius. And so with beta minus the alpha smaller than or equal to 2 pi, and it's a positive angle. Sometimes some things you might need to things that you need to find this area. Of course, you have to graph a curve to see what is the outer and inner radius. A lot of times you should use symmetry, and if you graph the curves correctly, you're gonna be able to see that symmetry immediately. And so you're just gonna apply them into it, and instead of finding a bunch of small area, if you see the symmetry, you can combine them all in once, and it's gonna save you a lot of time. And in some special case, you can even have like odd and even functions, and it can, if you also see it, say, the two area is immediately equal to one another, or if you have three different areas but at three different locations and they're separate, but you can see the fact that they equal to one another, then that's something you can use to shorten your interval of taking integral. Now let's work on the fourth example. Set up but do not evaluate the area of the region inside R equal sine 3 theta. So sine 3 theta is the red curves as we have, and outside of R equal half. And so these are the area that we need to find. These are the regions that we have to find the area of. Write the integral with the smallest possible interval of integration. And to graph this one, I use Desmos. It just save a lot of time for this kind of sections, but I would highly recommend you guys try to work on it and draw the graph on your own, because in the exam I don't think you can use any other software applications. Write the integral with the smallest possible. First of all, let's write what is the area. So the area is going to be, each of these is going to be half of whatever angle is here and whatever angle is here. And so to find these two angles is where you put you find the intersection between the two curves. Sine 3 theta is equal to half. Therefore, you have 3 theta is equal to sine of something is equal to half. You have it's going to equal pi over 6, and then you have it's equal to pi over 6, and then you have another one is 5 pi over 6. And so if you do replace that and you try to find theta, you have pi over 18 and 5 pi over 18. So you know these two intersections, and so it's going to pi over 18 to 5 pi over 18. And if you notice the fact this is going to be the middle, let's work on the actual area first. And so you have the outer radius be sine square 3 theta minus 1 over 4, which is half square d theta. Now, it's asking us to put it in the smallest possible interval of integration. And what it always means is that it's just going to try to make us to use symmetry to make sure that we only take the integral on a small interval, and we multiply it many times to make sure that it to get the area that we need. And so here, if you look at your free half of the loop, you're going to see the fact that each of the loop is comprised of two different area, the one in green and this one in green. Now if we shorten the interval of taking integration from here to here, this is pi over 18, and this point is going to be the middle point of your two angles. And to do that, I will put it as, you add them together and divide it by half, so it's 6 pi over 18 divided that. You're gonna have this one is pi over 6. And so if you want to shorten it, I'm just and then this one you multiply by 3. So you're gonna have 3 multiply half multiply 2, because you double this green area. And I'll put it back in blue again. 3 multiply half multiply 2. And so you can, now your interval shorten into pi over 18 to pi over 6. And you have sine square 3 theta minus 4th d theta. And so you can simplify this part and just put it as 3. And now your area is shortened because there's no further symmetry that you can see from this little part. Now, if you have any questions, as I always say, email me and let me know if anything. Last week I really appreciate some of you send me notice about what I make a mistake in the previous sessions. It means a lot to me, because it means that you gotta listen to my sessions and actually pay attention to it. Now, let's go to the last example of Math 141. Find the area enclosed by a loop of r sine 3 theta. I would say it's kind of like a small portion of the previous example, where you already find the where you can see the procedure is find the angles that is bounded by each of the loop. And so to do that, you can see the fact that what you're looking for is that you're looking for the angle theta that make it go back to 0. That's where you have the area of one loop. And so you're gonna try to solve sine 3 theta equal to 0 and try to find the smallest two angles that give us 0. And so it's gonna give us 3 theta equal to 0, or it's gonna equal to pi, or you're gonna have theta equal to 0 or pi over 3, and that is the two smallest angle that going back to 0. And so the area enclosed by a loop is going to give us half of 0 to pi over 3. Outer radius is sine square 3 theta. Inner radius is nothing, and so you're gonna put it at 0. So that one is 0 d theta. On the other hand, you can also shorten the interval of integration if you can use symmetry here, as very clearly shown in the previous example. So you're gonna have half multiply 2, the integral from 0 to pi over 6, sine square 3 theta d theta, or you're just gonna have this integral. And so again, this is another case where you come to use symmetry, but I'm showing this because It's as an exception where you have your inner curve be r equals 0 or no inner curve at all. And so that's example 5. And let's go to the last example. Set up but do not evaluate the area of a region inside both curve. And so inside both curve is where you're gonna have this part and this little curve here. And so to do that, let's find what is the angle bounded this part. And to do that, you set these equal to one another. And what you end up having is that sine theta equal cosine theta. Now let's see if you have like a regular angles, what regular circle and what angle is going to give you these two sine theta equal to cosine theta. And remember, this is the cosine angle and this is the sine angle. It can either be this point or this point, right? Because it's where you have y equal to x or equal passing one another, or also sine theta equal cosine theta. And so it's where you have theta equal to pi over 4 or 5 pi over 4. So it's cutting one here and one in here. And this is where you have at 0. Pi over 4. Oh, to identify which point is which point, you need to identify what is the first point of and the terminal point, and the directions of it goes for each graph when you increase the angle. And so here, when you have pi equal to 0, theta equal to 0, this is the first point, and when theta equal to pi over 4, you're gonna have is equal to 1 plus square root of 2 over 2. And when it go back to pi over 2, it's going back here. And so this is the direction of goes for cosine, and this is when you have pi over 4, pi over 2. This one is going to be 5 pi over 4. And you can try the same thing for 1 plus sine theta to identify these angles as well. And so we have the area that we have is going to be bounded by from this point to this point. And so this point is where you have it come back to pi. So you're going from here is at 0, going to, when your angle is 0, going to pi over 4 and going to pi. And so your area, first of all, the big one is from pi over 4 to pi of the outer curve is going to be, this is going to be, I'm going to use symmetry here because these two are exactly the same as one another. And so it's going to be half multiply 2. This area from here to here with of the outer curve be 1 plus cosine theta square minus 1 d theta. And I'm going to use symmetry again for the other one. So you have plus half multiply 2 from pi to 5 pi over 4. The outer curve be 1 plus cosine theta square d theta again. Or you can actually combine them together. It's the area from pi over 4 to 5 pi over 4. 1 plus cosine theta square minus 1 d theta. Or if you want to do it in the other side using sine theta as the outer curve, then you're gonna have is equal to from let's see the starting point of sine, and so when theta equal to 0 is starting at 1, so it's starting from here. As you increase theta up to pi over 2, this is pi over 2. So this is where you have 0. And so for sine theta, if you want to find the, and so if you find what is the angle here, pi over 2, This one is going to give us it's -1. And so you can do this one's where you have pi, and this is where you have 3 pi over -3. This is where you have that when it cuts again, so you have this one's going to be 5 pi over 4. And so if you use sine, there are two ways you can do it. You can starting with you can find this individual of them, or you can start with, so 5 pi over 4 is another way to rewrite it as is -3 pi over 4, because when you add them together, or when you add 2 pi to -3 pi over 4, you end up having 5 pi over 4. And so I can just take the integral from -3 pi. Basically, you go from this point straight to this point, and you multiply by 2, so the half cancel out, and then you have 1 plus sine theta square minus 1 d theta. Actually, I don't even know why I minus 1. You don't have need to I minus 1, sorry. Because there's no inner curve at all. I think I miscopied my answer from my sheet. And yeah, but then this is the way you're gonna solve it. Try to use symmetry as much as you can and identify what is the inner and outer radius and what boundaries of theta are you talking about for the two curves that you're given. Now, I have some practice problems here, and I'll upload the slides shortly. And if you have any questions with any of these and you don't know how to find them, email me and I'll get back to you as soon as possible. If there's nothing else, thank you for listening, and I'll see you guys next week. Please try to do the practice exam as soon as possible, because there I can try to pick up some problems that people get wrong and resolve it for you in the final exam review.